Welcome to the All You Need to Know About Volcanoes, so AQA spec. You can use this video in one of two ways. You can either listen and use it as revision notes, or you can actually make revision notes from what I'm about to say. So divided it into different categories, and obviously the screen shows you the detail of each of those categories. So here we go. So number one, nature of the volcanic eruption. First thing is lava flow. Two types of lava generally. Fast running lava, which is basalt lava. Slower lava, which is more viscous, more sticky, which is andesite. You also get ash. You also get volcanic bombs, which are chunks of magma which are thrown out of the vent. Together they're known as tephra, so they're the bits of material that comes out of the volcano. You've also got heat and gas, and together all of those four make up a pyroclastic explosion, which is also known as a AQA A. That can come out of the vent or the side of the volcano. Also, you can get acid rain during an eruption or after. Also, another characteristic, because that's what nature means, are submarine volcanoes, so underneath the ocean, volcanic islands, or potentially volcanoes on continents. So let me just hotch the page along a little bit. So secondly, how is volcanicity created? So get used to that word volcanicity, because that's what AQA potentially could use here. So three types of areas. Your constricted plate margin, where you've got oceanic crust pulling apart, fissure shield volcanoes there. Or continental and continental plates pulling apart, like in Africa, where you get your stratovolcano, a little bit more explosive. Destructive plate boundary, oceanic crashing into oceanic, submarine volcano originally, but then would go into a stratovolcano once it had poked out above the surface of the ocean, or oceanic crashing into continental, that'll be on continental crust, and again you'll get a stratovolcano there. Then finally, magma plumes, hotspot like in Hawaii for the oceanic crust, shield volcano, or underneath your continental crust where you get your supervolcano like in Yellowstone. Then we've got all the hazards. So this is quite a big part of the page, so what I'll try and do is move the page along as I talk you through it. So forms of hazard. First one, obviously lava flow. It's a primary hazard. Remember what that means. That's the first thing that pops out of the volcano. So obviously molten rock. Again, the two types. So runny, the basalt, tend to get that at a constricted plate boundary. Magma escaping due to that gravitational sliding and pulling the plates apart. Or it's at the Rift Valley at the constrictive, so like Africa, where the Rift Valley drops and the magma is obviously nearer the surface, so therefore the magma tends to find its way to the surface and cause a volcano. The right-hand side is talking about the predictability or the scale of this hazard. So predictability, it's partially predictable. More on that in a minute. Scale would be local, though, for lava flow. So second hazard is your pyroclastic explosion, or sometimes called pyroclastic cloud or flow. AQA A is another name for it. Basically, it's a glowing cloud of heat, ash and tephra. So the tephra, obviously the bombs and the ash, and a little diagram there just kind of showing you it shoots out of the top and can roll down the side of the volcano, mainly due to the fact that magma is full of gas, so therefore you get more of an explosive hazard. Is it predictable? Partially predictable. Again, more about that in a minute. Slightly larger scale, because you've got ash involved, it could potentially be global, because the ash could be sent higher into the atmosphere. Third one, we have forgot to say, sorry, pyroclastic explosion is primary, so it's the first thing that comes out of the vent at the top. Third hazard is a mud flow, also known as a lahar. Secondary hazard, because it happens after the explosion. Other things need to happen for that to kick in. So let me just flick slightly to the right there so you can see it all. So flowing liquid ash, basically, so ash plus water. Where does the water come from? Could be rain, could be a river, lake, melted ice or snow. Partially predictable, because if you've got water nearby, that's a potential that it might happen. Scale of it is regional or local. Then we move to our gas and acid rain. I've bunched those together. Secondary again, in the atmosphere, obviously you've got the gas, but the gas could well be the CO2. That would mix with the water, i.e. rain, and potentially cause acid rain. Is it predictable? Possibly. If you're going to have rain at the time of the eruption, that might make it more predictable. Regional, national, or even global, because the ash that's sent up into the atmosphere could fall elsewhere, potentially creating condensation nuclei, potentially causing rain. Next one is a landslide. Again, it's secondary, so it gets kicked off after the explosion. So basically it's slope failure. So the ash slopes could be disrupted, or the explosion creates the actual movement of the landslide. Is it predictable? Partially predictable. It depends what your slopes of your volcanoes are like. Are they, do they have the potential to be disrupted? Local scale for that one. Then we get to fire. So fire, obviously the heat of the explosion or the magma would just ignite whatever it is there. Is it predictable? Partially, if you've got magma or you've got the pyroclastic explosion, then potentially if you've, say, got a wooded area or even buildings, that could be a potential hazard. Local scale for that one. One more on this page. Flooding, secondary, so the lahars could create the flooding or any displacement of water, so from a river or a lake from the explosion. You also get something, and I'm probably not going to say this right, Jokulhups, that's how you spell it anyway. I think that's an Icelandic word, where you get glacial meltwater, so the heat from the eruption melts glaciers, and that will cause obviously quite a bit of flooding there. Partially predictable, so again, if you've got water nearby, that's why that's partially predictable. Local scale for that one. Right, let's get on to page 2. I've got three more hazards for you there at the top. So tsunami, how could we forget that one? Secondary hazard, basically it's a tidal wave at the coast, isn't it? So, you know, how might that happen? Volcanoes can kick them off. So a landslide from the explosion or lava flow into the ocean. If you've got displaced water, then you will get a tsunami. Partially predictable, because if you've got a volcano next to the ocean, that's why that could be partially predictable. Regional, national, global scale, depending on where the slope of the volcano is and where the tsunami wave heads to. Climate change, so obviously what's that? Heating of the Earth's temperature. CO2 naturally emitted from volcanoes. Bigger the explosion, more the CO2. But you're looking at there, surely, your greenhouse effect, but the natural element of that. Is it predictable? Partially, if you're going to have volcanic eruptions, and obviously you're on a global scale there. The final hazard, weather could be affected. So ash in the air could block out the sun. Maybe even the ash creates condensation nuclei, so maybe you might have more rain. Again, partially predictable if the eruptions happened. And a lot of these secondary ones, you can potentially then predict them days later or maybe hours later. Local, regional for that one. Right, next big heading. So let me try and get that all on one screen. There we go. So magnitude. This talks about the size of something. So the magnitude of a volcanic explosion is measured by the Volcanic Explosivity Index, the VEI, which is universally used. The scale goes from 0 to 8. Naught is a small explosion, and these can happen daily. That's such as an Hawaiian explosion, which would be, to be fair, VEI of 1. That would be the type of volcano of a shield or a fissure. So shield like you get in Hawaii, fissure like you get in Iceland. Little diagram there, low volcanic shape, hence you just got a kind of a little slight kind of hill there. Lava fountain shooting out the top. That would be quite characteristic of a low value on the VEI. VEI of 8 though is very, very different. So we're talking about a very large explosion, very rare, thank goodness. Name for that is called an ultraplinian. Stratovolcanoes have the potential to be that explosive. And another classification there is that explosion will be called a megacolossal explosion. And I've drawn you a little diagram there. So classic volcano with the vent, with a big pyroclastic explosion. And if I just hotch the paper along a little bit, you've got that being 25 kilometers high potentially. So we're talking about a really, really big explosion. So thank goodness they're rare. So fifth section is frequency. If I just pull back a bit, you might be able to get most of that in, yeah. So frequency, small eruptions, very frequent. That means daily, up to kind of yearly. VEI equivalent for that tends to be 0 to 3. Where would they happen? Magma plume, so Hawaii, and constructive plate boundary with the fissure or the shield volcano. Very large eruptions are rare, so anything from say every 100 or every 1,000 years, or even every 100,000 or 10,000 years. So the time scale could be quite big. VEI 5 to 8. I've put destructive there and I've put strato, but what I have actually missed out there is it could be at a magma plume as well. So where you have a magma plume underneath continental crust, so like in Yellowstone, the potential for a very large eruption is potentially there, and that would be over thousands and thousands of years would be the distance between an eruption like that. Or you may have a dormant volcano that then becomes active. So within these kind of eruption cycles, so if it's say erupting every 100 years, that would be a cycle of activity. So it'd be dormant for some years and then it would be active. Or it's completely extinct because you've got no magma reservoir. Right, we're nearly there. 2 more sections to go. So again, let me try and get all that on one shot there, kind of there. So predictability. You can predict when a volcano may erupt up to a point. It is not a precise science, but there is more predictability than an earthquake. So why is that then? Before a volcanic eruption happens, you get some activity. So what might you get? Small earthquakes. Why is that happening? The magma is rising from the magma reservoir into the volcano. So that will just give us small tremors. How is that monitored? Seismometer, obviously. Other side to that, large earthquakes. That tends to be associated with the magma rising, but there's a huge amount of gas in there. So again, seismometer will potentially pick that up. Third precursor is ground deformation of the volcano. So maybe bulging on the side of the volcano. The way that would get picked up is you could put tilt meters, which are kind of monitors that you'd put on the side of a volcano, just picking up movements. Satellite imagery could do that, and also drones can be sent up to daily, hourly to pick up differences in the land shape. What else could happen? Gas emissions. So due to the magma building up in the vent, gas could be spewing out of the top. And again, how do you pick that up? Sensors on the volcanic slopes, or again, even drones with some maybe equipment picking up levels of gases. And then the last one is the ground actually heats up because the magma's rising, the magma's nearer to the surface, so the ground could potentially heat up. How do you monitor that? Thermal monitors, again on the volcanic slopes, or heat cameras fitted to drones or satellite imagery that picks up these heat spots. So that's why it's slightly predictable, because these things may be happening months, maybe even years before a particularly large eruption. Final section, nearly there. Challenges of volcanic eruptions. So AQA love this challenge question when they're talking about physical geography topics. So what would be the challenge in responding or just dealing with an eruption? Quite often volcanoes are in mountainous areas, so actually quite inaccessible for rescue teams and aid to potentially get there, even in richer countries. So it's more about a natural factor as opposed to a development factor. Second challenge, lava flows could block the roads, hamper the rescue vehicles. Same with ash and an explosion. So roads could be blocked, ash could be potentially deep on the ground and not enable ambulances, etc., to get there and rescue people. Ash could be still in the air, so helicopters and planes, it's very difficult for them to fly. Landslides could block roads, so that could be from the pyroclastic explosion. And then your mud flows, your lahars, again, they can block roads for many miles away from the actual volcanic activity. So I'm hoping that's helped you with your volcanic all there is to know.